This is a very interesting question on electromagnetism, especially for people in grade 11. To answer this question, you need to have a basic understanding of four things. The first one being Faraday's law of electromagnetic induction, Oersted law, Lenz law, as well as the right-hand rule, or sometimes I like writing it RHR for your notes if you're making them, for a solenoid. So be aware, there's the right-hand rule for a straight current carrying wire, and it differs slightly for a solenoid. I tell you, if you understand these four things, it will make your journey in electromagnetism quite easily. And I'm going to briefly talk about them as we attempt to answer this question. The first thing we have to understand is Faraday's law of electromagnetic induction. So what does it say? So this is the definition or the explanation of Faraday's law of electromagnetic induction that you need to learn, and in most of the time you will be asked to state this law. So what does it say? It says that the magnitude of the induced EMF across the ends of a conductor is directly proportional to the rate of change in the magnetic flux linkage with the conductor. So that is Faraday's law of electromagnetic induction. Now this feels like a lot of English, but as we move on with the video, you will start to see what this law implies, right? So sometimes in physics you may not understand the law itself, but it's important to understand what does it imply, what does it mean. So it talks about an EMF. So we represent an EMF or an electromotive force using this Greek letter epsilon. It's a funny looking E. So that EMF, they say that EMF is directly proportional to the rate of change in the magnetic flux. So there's the change in magnetic flux, where this triangle means the change in its delta, and this phi represents the magnetic flux. So the EMF is directly proportional to the change in the magnetic flux. If this increases, the change in magnetic flux increases, this will also increase. The rate, when we talk about the rate of, it means at the bottom we are essentially dividing by the change in time. But even if you don't necessarily understand what this law means, know the formula, also memorize this if you must, but it's important for you to understand what it implies. And I'm going to tell you just now what this law implies. So Michael Faraday made a very interesting discovery. So let's say you have an iron core, represented by this yellow, by this orange paper. Then we have a conductor, a wire that's able to conduct electricity. It means current can pass through this wire, and that wire is represented by this shoelace, right? So we've wrapped the wire around an iron core, wrapped it so that it makes a number of turns. So here maybe we would say it's 1, 2, 3, 4, 5, 6, 7 turns. So this will represent the N in that formula that we just studied, the number of turns. So this N tells us how many coils or how many windings or how many turns, coils, windings, depending on a book that you are using to study. They may be described differently. So that is the N. So what did Michael Faraday discover? Michael Faraday had this wire and connected this wire to a galvanometer represented by G, capital letter G. So you connect it there. Let's say now it's connected. What does this device do? It measures current. It measures electrical current. Be aware there's nowhere where I have connected a battery at all. So then you connect this device that is able to measure the current as well as the direction. So positive or negative to tell us the direction of the current. So if it's in the positive, it will be, if it's in the positive, you have a hand there pointing in that positive direction. If it's negative, then this will go in this direction, right? So what did he discover? He discovers that if you take a bar magnet with a north and a south pole, if you take that bar magnet and you start moving it, let me do this, you start moving it in and out of near your wire or near your iron core wrapped in a conductor, something happens. He starts noticing that hand, initially it's at 0, then I start moving this thing, and then you see that it flicks, meaning that it detects a current. But where is that current coming from? Because there's no battery, but there the galvanometer is registering a current. When maybe he moves this bar magnet away, he sees, hi man, the direction of this current changes. So he keeps doing that, taking it in, out, seeing that there is current flowing in this wire. And if I bring the magnet closer, the direction changes. If I take it away, the direction changes. What on earth is actually happening? Where is that current coming from? And why does it change direction if I move it in and out? But he also picks up something. If he just places the bar magnet like this without moving it, there's no current that is being registered. And essentially that is the gist of Faraday's law of electromagnetic induction. A change in the magnetic flux linkage induces a current in the conductor, and that current is directly proportional to the induced EMF. But you may be asking, where is that current coming from? To answer that question, we need to go to the second law. And that law, we say it is Oersted law. What does Oersted say? Oersted says something very interesting. So we have induced a current in a solenoid because of a change in magnetic flux. The moment that that bar magnet was stationary, there was no current. But if we were changing it, it was in, out, there we registered a current. And I asked you, where is that current coming from? It's coming from the change in the magnetic flux. As I'm doing this, the intensity of the magnetic flux is changing. But the moment I'm doing this, there is no change in that magnetic flux, right? When it's stationary. The second law that you need to understand is Oersted law. And Oersted law mentions something. Because why is there a change in the direction of the current that we registered? If we keep changing it, that direction of current was changing from negative to positive. If it was stationary, it was at 0. But why is there that change? So Oersted law tells us that an electric current creates a magnetic field. So one, we have induced an electric current in our solenoid by simply changing the magnetic flux. So now, if we have a current now, an induced current, that induced current itself will actually generate its own magnetic field. So it means now either here we'll have the North Pole or the South Pole, or it's the other way around. We have the South Pole here and the North Pole here. Because why? An electric current induces so maybe this side we have a South Pole, this side we have a North Pole. The other way around, It may be that this side we have a north pole or this side we have a south pole, depending on the direction of the current. This will just continuously change because the current that we have induced in here, the current that wasn't here, we've created it from just changing the magnetic flux. It creates its own induced magnetic field, and that magnetic field has a north as well as a south pole. But how do we know which one is which? How do we know if the north pole is here? How do we know if the south pole is here? Or how do we know if the south pole is here? Or how do we know if the north pole is here? We go now to the right hand rule. The right hand rule for a solenoid is slightly different to the right hand rule for a straight current carrying wire or conductor. So take your right hand. The fingers are going to represent the coils or the windings, the number of turns. And that is where your current is flowing, right? The thumb represents the north pole. So the thumb is the north pole, and the base of your fist, if you're holding it like that, is the south pole. So you have the south pole, you have the north pole. If I do it this way, you realize that now my north pole is all the way around. You just move it. So we have the north pole and the south pole. But how do we know in which direction is the thumb pointing? To do that, we need to know the direction of the current. We need to know where is the current going. How do we determine that? So I'm holding this with my right hand. If the current is in this direction, the arrows are pointing in this direction, like this. Where is my thumb? It means that my thumb, I said it will represent the north pole, and the base of my fist will then be the south pole. The moment this changes, you see that where my fingers are now pointing up, it means the direction of my current is now like this, up. Where's my thumb? My thumb is the other way around. It's here for the north pole, and the base is now the south pole. So this change will depend on what is the direction in which your bar magnet with a north and a south is moving. And I'll show you just now how it actually changes. The final piece of this puzzle is Lenz law, where Lenz says induced current opposes whatever change is happening. This law is the reason why for this formula here, we actually have a negative. Keyword there, opposes. So whatever is happening, Lenz law says induced current will oppose it. It's like, I don't want that to happen. So how does that happen? Let me tell you. So let's say you have a bar magnet with a north and a south. You are bringing it closer, meaning you are inducing a current. You induce a current in here. If there's a current in here, according to Oersted law, it will generate its own magnetic field. So it will have a north and a south pole. You have this permanent bar magnet with a north and a south. You bring it in, induces a current in here through that wire, so that this thing also has a north and a south pole. But how do we know whether it's a north or south here? If you're bringing it in like this and you are bringing the north pole closer, according to Lenz law, the induced current will say, nope, I oppose that change. What will oppose a north? Think about it. From grade 10, it will actually generate a north pole here to say, nope, I don't want you to come. It will repel. However, the moment you take the north pole away, it's like, no, come back. Where are you going? Then it induces a south pole. A north and a south attract, and a north and a north repel. So let me do it again. So you bring in the north pole, and then there's an induced current. This induced current develops its own magnetic field, and because of Lenz, it opposes whatever change in the incoming magnetic field. So if a north is coming, it says, nope, I don't want you. It generates a north pole. The moment you take the north pole away, you like, it's like, no, come back. It creates a south pole. Similarly, if you're bringing in a south pole like this, there's the south pole. It will generate a south pole to push, to oppose the change that's happening. The moment you take that south pole away, it's like, no, come. Then you will have a north pole. I hope that is clear. So if you have a north pole here, it essentially means you have a south pole on this side. And if you have a south pole here, it means that you'll have a north pole on the side. And this thing will behave like a magnet. And you can draw those magnetic field lines around it. Now that we are here, we can actually go and answer that exam or test question. Let's have a look at this question properly now. The diagram below shows a bar magnet that is dropped vertically downwards into a stationary coil. The direction of the current induced in the coil is shown. So you're given a bar magnet. This is the bar magnet. So you have the bar magnet here. And this bar magnet is dropped. That's why you have that arrow there. It's been dropped into this coil. This is some sort of perhaps a solenoid. So that is the coil. And you can also see here a circle with a big G in it. That's a galvanometer. Like I said, it will be able to detect the current I as well as the direction. Now, additionally, at the bottom, here is the same bar magnet because it was dropped and it's now moving away. It's moving away now. Away. So what then are the questions? So you know that a bar magnet has either a north or a south. So X can either be a north pole or a south pole. Then we go down. Question 2.1. State Faraday's law of electromagnetic induction in words. And that is a 2-mark question. Please write these questions down as I will not show this question again. I'm just going to answer all of them at once. 2.2. Determine the polarity of the bar magnet at X. So is it a north or a south pole? That's what they are asking us to do. It's also a 2-mark question. What is the polarity of the coil at Y? Let me show you where Y is. Here is Y. Remember, if there's a current being induced in this wire, it will also have its own north or south pole. So it will behave like an electromagnet. So what is that polarity at Y? Is it a north or is it a south pole? This is also a 2-mark question. This question is more theoretical than calculations. So let's try to answer this question then. So question 2.1 required us to state Faraday's law of electromagnetism in words. And that was a 2-mark question. So essentially, this is what you will need to write. You'll say the magnitude of the induced EMF across the ends of a conductor is directly proportional to the rate of change in the magnetic flux linkage. And if you write that, you actually get your full marks. So this is the setup that you are given in the question. You have your solenoid, which will behave like an electromagnet. It means that as you moving in this bar magnet, that's why the arrow is pointing, it's coming in. It will induce a current in here, and that current in turn will also create its own magnetic field. We also have another bar magnet that is moving out away. That's why that arrow is facing in that direction. So we need to now tell is this the north pole? Is X the north pole, or is X the south pole? So that's what we need to determine. If X is the north pole, it means here we'll also have a north pole. And essentially that would mean here is the south and here is the south pole. So how do we determine this? To do this is quite straightforward. You just use your right hand rule. You're saying, okay, if you look at the arrows on the question, they are pointing down. So it means your right hand is going to be like this. If your right hand is like that, it means here on the solenoid we'll have the north pole. Trying to see where I wrote my north pole. I can't find it, but it is fine. So it means here we'll have, for the electromagnet, we'll have the north pole. But we're not done answering that question. If we have a north pole here for this electromagnet, let me write it down. Can't find a marker. So if we have a north pole here, and we have a bar magnet that's coming, so this north pole is for the electromagnet. We have a bar magnet that's coming. According to Lenz law, the pole here will be because of the induced current will oppose the change. So if it's coming in, it will say, I don't want this change. And the only way that could happen is if we also have a north pole here at X. They will oppose each other because it is coming in. If this perhaps was moving away, then we would say it is the south pole. So it means the polarity at X will actually be the north pole. It also means here we have a north pole. The second question after that is asking us to say what is the polarity of the coil at Y as the bar magnet exits the coil. So as this bar magnet is going away, shown by this direction, what polarity will be here? Think about it. What polarity will be there? If this is the north pole, this is the south pole, and this whole magnet is actually moving moving away, what polarity will be here? According to Lenz law, the polarity here will be in opposition. If this is going away, it will say, I want you to come back, and hence induce a north pole here. So that a north and a south will attract, a north and a north will repel. So we've answered both of those questions. If you have any comments in terms of how you would go about answering it, please let me know. I would actually appreciate hearing how you guys go around solving these types of problems.